All right, here. Let's try another video solution from 13. And this says a nuclear fusion. Oh, this is going to be a fun discussion near the very end of Physics 111. So when we get into modern physics, we learn about nuclear reactors, nuclear fusion, and the energy and all that. So for those of you who haven't been exposed to modern physics, you're in for a real treat when we get to chapter 28, but that's still a ways down the road. But this one is saying in nuclear fusion, the energy source for our sun, it's also the energy source for the hydrogen bomb, it's also the energy source for fusion reactors. It says occurs much more readily when the average kinetic energy is high. So this happens naturally in the sun because the center of the sun is 15 million degrees Celsius, or just 15 million Kelvin, as I mentioned in a video solution earlier, that when you get to those big numbers, whether you add 273 or not, it's kind of just insignificant. So again, the center of the sun has a chemical a nuclear reaction, 15 million degrees, which sounds really high, and I get it is, but it's actually kind of low in terms of nuclear fusion. I would suspect we won't quite get into the engineering. We'll just kind of talk a little bit about the physics of it when we get there. But I know in my engineering class we spent some time because even 15 million degrees, nobody is going to try to engineer a fusion reactor on Earth at such a low temperature of 15 million. I mean, we think about the sun, we think it's hot, but the nuclear fusion barely takes place. You only get away with a lot of energy because the sun is so big, and so the energy concentration is small. In fact, kind of a fun statistic is your own body, for its volume, gives off more thermal energy due to metabolism than the center of the sun does for nuclear fusion. There's just not much energy per volume given off by the sun. It's barely getting any nuclear fusion going on. Like I said, it's only 15 million degrees. That's why all these next generation fusion reactors, the tokamak reactors, they're all trying to achieve 800 million degrees, at least for a short period of time, so they can have this reaction for a short period of time. And ITER is kind of the latest and greatest experiment. Anyways, but I digress. I apologize. I just got so excited here about nuclear energy, nuclear fusion, and maybe a good alternative energy in the future. Anyways, it says here, occurs much more rapidly when the average kinetic energy of the atoms is very high. And that's what I was saying. We need it really, really high. Barely works at 15 million. Prefer to have 800 million. That is at high temperature. So suppose you want the atoms of your fusion experiment to have an average kinetic energy of, and so I'll put kinetic energy equals 6.40 times 10 to the minus 14 joules. Okay. What temperature is this? Well, I hope you kind of caught that as we were dealing with this, we said that the kinetic energy of the atom is related to the temperature through this little calculation. It's called the, what is this? The equal energy partition theorem. Which is a fun discussion in itself. But your author then used this to equate velocity to temperature, and that's what I did. Now, it sounds like we don't need to do this because we already know this one. There's no point in looking up the mass or the velocity or trying to figure it out. Collectively, we know that's the kinetic energy. So this is 6.4 times 10 to the minus 14 joules. And then, of course, Boltzmann's constant is the 1.38 times 10 to the negative 23 joule over Kelvin. And then the temperature. So here we can cancel off the joule, rearrange the unit, and we're going to have the temperature in Kelvin. As makes sense, we should, given that we're equating motion with a temperature. That can only be done on the Kelvin scale. All right, so let me take this 6.4 times 10 to the negative 14, which again is an enormous amount of energy for a little tiny atom, which is why the temperature is going to be so high. It doesn't sound like it when you say 10 to the minus 14 joules. But it is. Let's finish the calculation. So times 2 and then divide by 3 and then also divide by Boltzmann's constant. And that's the real one. Look at that, 10 to the minus 23 downstairs is going to give me a temperature of, and I'll call it 3.09 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this would be, I'll write it in millions, 3,090. So then we would still have 10 to the 6th Kelvin. That's millions of degrees. So this is 3,000 million degrees. And so they're just hoping to get around 800 million. So it seems to work pretty good at 800. That's kind of the start of where the reaction really starts to take off. Higher would be even better. This would be amazing, but I guess that's what they're having us go to. But if I understand the engineering right, they're really trying to shoot for this, because if you made a graph of reaction rates, and so I'll say rate versus temperature, kind of ramps up and levels off a little bit at 800 million. So going up beyond that is more of a challenge without much gain in reaction rate. But hey, we'll take anything we can. I mean, if you can get it that high, great. But hard to hold things together when they're that hot. They just melt. All right. Take care.